All right. Can you hear me?
Yep, I got you.
All right, excellent. So good afternoon. Uh, Again, I'm Matt Bellhorn, a member of the OLCF User Assistance Group, and this talk will be about using Python and best practices and recommended approaches using Python on Summit and our other IBM Power 9 systems. So first, a picture of what a normal Python environment can end up looking like, courtesy of XKCD. Uh, Python environments, even on a local machine, if you're using more than one version or have special requirements, can get out of hand pretty quickly. This is even more true on HPC resources. Um, we'll try to unwind this mess and show you how you can avoid this uh, with the Python interpreters and environments that we offer. Um, Python, of course, is supposed to be easy uh, and can be uh, as long as there's some steps taken to avoid convoluting your Python environment on machines like Summit. All right, so how do we offer Python on Summit and our other machines? We do this in three different ways. The first way, and the way that I'd recommend for most users, is to use Anaconda distributions. Uh, we provide a set of Python environments derived from Anaconda that contain within them by default uh, most uh, maybe not most, but a good cross section of commonly used Python extensions beyond the Python standard library. And these Anaconda distributions are easily extendable and customizable if there's something that you need that's not in the prepackaged environments that we offer. On Summit and the Power 9 machines in particular, um, we also offer uh, uh, IBM's Watson Machine Learning Community Edition, uh, which is itself a Python environment based on Anaconda, uh, but it is enhanced with machine learning tools and frameworks preloaded in that environment that are optimized for Summit, IBM's AC922 hardware, and modified to run at the scales available on Summit. Uh, just like a generic Anaconda distribution, IBM WMLCE is extensible through cloned Anaconda environments. We'll try to do that and more on it in a separate talk specifically about machine learning. And then the last way that we provide Python is through minimal Python interpreters that are accessible through the environment modules. Uh, there's no there's no real set of Python extensions preloaded in these environments, but in the base installations of them, we provide enough tools for you to create a virtual env of your own if you're more familiar with virtual envs and more comfortable building your own Python extensions from source or from the Python package index rather than relying on the pre-built binaries in the Anaconda repository for PowerPC 64 LE machines. So I'm going to go through each of these. Actually, I should back up one moment. There's also the Python that is provided by the OS. That's very minimal. It's not extensible. We can't modify it because it's part of the node image. But it is there. If you just need a Python interpreter, it's always available. Most people who are using Python need some additional extensions. And so that's what these other distributions that we provide offer. Okay, so how to use each of these. They're all exposed to the environment module system. In the case of our generic vanilla Anaconda distributions, the module files for them are named Python, and then the Python major, minor, and micro version. They'll have Anaconda and the Python major version, and then an integer denoting successive releases as the environment's been patched. We generally don't remove software from the machines, so if someone's using it, it'll always be available. But if we have to fix something, we will install an additional copy of that software and make it the default. In the case of Python Anaconda environments, those subsequent re-release of the same environment will have a suffixed release number. Each of these environment modules for vanilla Anaconda set the Python user base to unique location. So as mentioned before, the home directory is shared on all of our machines. By default, Python will write and install packages installed in the user scope into their home directory under .local lib python major.minor version / site packages. However, because home is shared on all of our machines with different architectures, if we allowed Python to do that, you'd have potentially a mess of modules that depend on compiled C code in the Python path on all of the systems that may or may not run on the machine that you're currently running on. So we modify Python user base so that packages that are installed when one of these Anaconda modules is loaded into your site packages get put in a unique directory for that instance of Anaconda and that machine and its architecture that it is intended for. Anaconda relies heavily on precompiled binaries. There is in Anaconda's repos channels that support PowerPC 64LE, Power 9 architecture. And as time goes on, more and more packages are available for Summit's architecture in those repos. However, there's a chance, and a couple years ago, there's very few packages available for PPC 64LE in Anaconda's repositories. There's a chance that a package that you may want is not in those repos. And there are some ways to work around that, which we'll talk about later. But it's useful to keep in mind that stuff that you install for Anaconda through the command line tool Conda are generally similar to wheels, Python wheels, and rely on precompiled packages, especially if they require some sort of C code, compiled C code for that extension. Anaconda environments can be extended and customized from the default base environment that we offer through use of the Conda command line tool. Conda is similar to pipenv, so it's both the package manager and the manager for virtual environments all in one utility. And we'll show some examples about how to use it if you've never seen it before or are not familiar with using Anaconda. IBM Watson Machine Learning is also an Anaconda environment, but as I'd mentioned, this is preloaded and pre-populated with machine learning tools. TensorFlow, PyTorch, Caffe, Keras, Dask, Spark, scikit-learn, IBM's distributed deep learning package, DDL, SnapML for use with Spark, and many others. We'll have a separate talk, I believe right after this one, by Junki Yin, They'll go into detail about machine learning tools on Summit. The module files for IBM Watson Machine Learning are named IBM-WML-CE, and the versions are the Watson Machine Learning release version, and then patch as bugs or issues in a release are identified. IBM will fix them, and we will renew and redeploy those environments. And again, they'll get a suffix patch release in their module file version. Just like in an Anaconda environment, it's possible for users to clone the IBM WML-CE environments. More information about this is in our standard documentation, docs.olcf.ornl.gov. We have a whole section about using IBM WML-CE, but the short version of how to clone the environment into a location that you can write to and modify if you want to add additional packages to it that are not installed in the base environment, is through the use of this command, conda create -p and a path to the location where you want to clone the environment. You can also use -n and a name. I generally prefer to specify a full path, take some configuration in a .conda rc file in your home directory to specify paths where just named environments would be installed. Path gives you fine-grained control about where those are located, whether it's in CCS Proj, on the NFS share, or on GPFS, the GPFS file system, or your home directory. And then, importantly, the -- clone and the name of the IBM WML-CE environment that you want to use as a base. And this will copy everything that's installed in the base environment into the clone, where you can modify packages, rebuild them, add additional ones, etc. Okay, and then the last way that we provide Python is through native Python interpreters. They're not Conda environments, just a Python interpreter. They're also exposed through environment modules. The module files are named Python, and then just the major, minor, micro version of that Python release. And on most of our machines, we have Python version 3.7, 3.6.6, and 2.715. Some of our other machines have some older versions of Python 3 and 2. And I would say I don't generally recommend using these modules. Go through why on this next slide. The reason I wouldn't recommend using these is because they are just a bare Python interpreter. And the extensions that we could provide for them are not co-installed in a single site packages prefix for that Python interpreter, which means that all of the extensions that you might want to use with this, if we've built them and installed them, are their own separate module files. And we are, a couple years ago, we got out of the business of building Python extensions and providing them via environment modules. It's really messy. It's not the way Python is intended to have extension packages installed, with everything being in separate prefixes and dumped into the Python path. So all that's provided in these native Python environment modules is virtual env, pip, setup tools, and some very low-level utilities for creating a virtual env that you can then populate with whatever you specifically want. And in most cases, the extensions that you would that many users would want are already in the Anaconda environments. So rather than go through all this and just load the default Python, which is full environment provided by Anaconda, and everything's already there. In order to load the environment module for Python, bare Python that's not Anaconda, that has virtual env and setup tools, you have to unload all compilers. So at any compiler module file you've got loaded, unload it, and then load Python major, minor, micro version through lmod to get the instance of Python that will let you set up a virtual env. And the reason for that is that makes sure that the only compiler that's in your environment is the OS compiler, and any packages that you install, we use that compiler in the system libraries provided by the OS to build and maintain ABI's compatibility with Python and other extensions that you'd build and put in this environment. There are, if you're going to use these modules, a couple of Python extensions that we do provide, and we might consider adding environment modules for other extensions, but we really encourage folks to use Anaconda instead. And in most cases, if you want something that's not provided in these native Python environments, you'll have to create a virtual env and install those extensions yourself. Yeah, so this goes on. This is true for especially things like H5Py or PyNet-CDF, where these are bindings for compiled C libraries that are external to Python. In order to provide a module file for something like H5Py, it'd be necessary to make a specific choice about what HDF5 implementation to use. Some users might want 1.10.4, some users might want 1.18 or 1.8. It's not really practical to maintain an environment with these external dependencies for Python extensions through environment modules. And the environment modules that we do provide for Python extensions don't necessarily load their dependencies. So not external libraries. If a package depends on a library that comes from compiled C code, like HDF5, or other Python extensions, which it may require. So there's a lot of complexity in trying to use these module files. I would recommend using Anaconda or IBM WML CE instead. As far as providing your own extensions, you can install Python packages anywhere, as long as they get added to your Python path. But you want to avoid Python path pollution. So if you have installed Python packages in random locations, you want to make sure that when you're adding those paths, those directories to the Python path, that you're not mixing up Python interpreter versions, the language versions, or if it depends on compiled code, machine architectures, or other external dependencies. This is essentially the same problem as providing packages via environment modules. It's very easy to pollute the Python path and wind up with a really corrupted Python runtime environment. So I don't really recommend installing extensions just wherever you want and then adding the Python path. I recommend using a virtual env or a conda env, where all the extensions can be installed in a single site packages directory for a specific Python interpreter and managed either through virtualenv for Conda uh, and this will allow you to maintain a clean and isolated Python environment. All right, so how to create a Conda environment. We'll start there because as I said a couple times now, really recommend using Conda instead of the bare Python interpreters. Conda will, if a package needs external precompiled C code for an extension, it provides those libraries as well as the Python code. So it's almost like a small miniature OS. But Conda will pull in the packages that it needs from repositories, which Anaconda calls channels, and the binaries in these repositories are typically well optimized for the architecture that you're running on. If you're running on x86, 64, they're optimized for generic architectures for all sorts of machines. But for the PowerPC channels, these binaries are generally well optimized for Summit's architecture. If you're installing packages from the Python package index through pip, and it's pulling in wheels that maybe have been mislabeled as architecture independent, they might not work on HPC resources, especially if it pulls in precompiled code for an x86 architecture system. You won't have that issue with Conda, but you will have that. You could run into that if installing packages as wheels through pip. I recommend that if you're going to build packages, instead of relying on the precompiled packages from Anaconda's repos, that you build them from source. So here's a couple examples of how to create a Conda environment. Once the environment module for Python from an Anaconda distribution is loaded, it'll expose the command conda. And with that, you can conda create a set of packages that you want pre-installed in your conda environment. Optionally, -C and list of channels if you don't want to use the default or want to pull packages from a specific channel that you know that's not a standard one, and -P the path to where the Anaconda environment should be installed. And as I had mentioned in the programming environment talk, I generally recommend installing these things to a location that's not purged. So something like CCS proj, your project ID. To use the environment that you've cloned, you want to source the activate script and then the path or name of the Anaconda environment. There's other ways to invoke this as well. There's there's a setup conda script. I'd stick with this one, but there's more ways than just what's shown here to activate the environment. Once it's activated, you can install additional packages from the conda repositories as if this was your local machine. So conda install numpy, pyaml, whatever you want that's in the repositories. Conda will install these packages, into a single site packages path in your cloned environment. So you don't have packages scattered around the file system and have to add them to Python path and potentially corrupt your Python runtime environment. If there's a package that's not in the Anaconda repos, you can install it from the Python package index or from source using pip or setup tools while the Anaconda environment is activated. So you don't inadvertently pull in incompatible wheels or precompiled packages in the Python package index. I generally recommend building things with the -- no binary flag if you're installing them through pip. So for example, this line would install MPI for Pi in your active Conda environment. And it will download the source and build it using MPICC that it finds in your environment and make that available. When you want to deactivate the environment, activating it puts a shell script in your active terminal session called deactivate. Source deactivate will undo all of the path environment changes that source activate does, and allow you to access either the OS provided Python interpreter and user bin or others. If you're going to use virtual envs or VEMs, as they're known in Python 3, it's similar to what Conda does. It provides an isolated Python environment. But if you're using Python 2 versus Python 3, there'd be two different ways to create a venv. For Python 3, venv was removed from its own standalone command line tool. So you have to invoke it as Python 3 -m venv and the path to where you want to create the virtual environment. Python 2, there's a command line tool that does this virtual env from the path to where you want to create the environment. You can activate a virtual env in several ways, either by sourcing the path to where you created the environment, and then under that, in the bin directory, an activate script that will put a shell function in your environment called deactivate that you can call to end the environment. Or if you have a Python script, and this is especially convenient for Python codes that run on the compute nodes, you can, in the shebang line of the script, put the full path to the Python interpreter in your virtual environment. Invoking the Python interpreter that exists in a virtual environment will implicitly activate that environment for the code that it executes. If your Python, if your virtual env requires external packages to satisfy dependencies like HDF5 or MPI, you want, I would recommend that all environment modules be loaded first before you activate the virtual environment. Both lmod and this activate script make changes to your environment, and so that they don't collide. You don't want to make these changes in a first in, last out way. So load all the environment modules that you want first, then activate the environment, the Python environment. And if you want to change environment modules, deactivate the virtual env before doing so. Building packages from source. This is going to be tricky, especially if it's got external dependencies. So it's easier to manage this at a personal level than for site and provided environment modules that work for everyone. you can install packages either using setup tools, Python setup.py install, or pip. In most cases, can install packages from source, again with the -- no binary flag. And in general, most packages will have a set of environment variables that allow you to control details about how a package that depends on external compiled C code will be built when installing it through pip. But to find out what those are, you have to check the documentation for the package that you're interested in. The backup slides in this presentation have some recipes for things like HDF5 and MPI for Pi and others as examples for how to do that. General guidelines. I would highly recommend following PEP 394. Python 2 is officially deprecated as of the 1st of this year. So eventually I expect PEP 394's recommendations to change. But in short, what it says is that if you are using Python 2, invoke the binary as Python 2. Or if you're using Python 3, invoke the binary as Python 3, instead of using the ambiguous command Python, which depending on how the interpreter was installed, could be 2 or 3. Same thing in scripts. If using this shebang line, pulling Python from the environment, user bin env, call out specifically which version you need, Python 2 or Python 3. But because Python 2 is deprecated as of the 1st this year, I recommend that codes that are still using Python 2 make a serious effort to migrate to Python 3 if possible. And then, of course, Python environments, mixing Python environments doesn't really work. If you're using a conda env, use a conda env. Don't try to activate a virtual env while you've got a conda env loaded. Don't try to invoke the OS Python interpreter while you've got a conda env loaded or virtual env loaded. Choose one and stick with it. If you're using a conda env or a virtual env, don't mix it with Python extensions that we've provided by environment modules. So ignore that pi-mpi for Pi environment module if you've got a virtual env loaded. Recommend just installing that package in your virtual env as you need it, or your conda env. And then reiterate, be careful with pip install -- user, which would put things in your home directory in general. Some of the module files that we provide modify the Python user base, but not all of them. So you want to check that Python user base is unique to the Python version and machine architecture that you're using. And if not, set it to something unique, and you have to set it to that unique directory each time you want to use or install packages using pip install -- user. If you're using a conda env or a virtual env, you don't need to do this at all. You can just pip install packages directly into that conda env or virtual env and clear up any potential source of confusion or environment corruption. So that's about all I have time for, I think. I think I've gone a little bit over. But if there are any questions, I'd be happy to answer them. And the backup slides here do cover more things than I could squeeze into this short talk.